Okay, hi all. Let's start this week's seminar. We have the great pleasure to host Efstathios Charalampidis from San Diego State University. Let me say a few words about Efstathios. So he did his bachelor in physics in the Aristotle University in Greece. Then in the same university, he did his Master of Science in computational physics and his PhD in applied mathematics. Then he moved to the University of Massachusetts, Amherst, for a postdoctoral research assistant, and then she changed to a visiting assistant professor, and finally I became a lecturer and chief undergraduate advisor to 3 months. Afterwards, he went to California Polytechnic State University, San Luis Obispo, where he was an assistant professor, and in fact, very recently he moved to San Diego State University again as an assistant professor in applied mathematics. His research interests revolve around computational and applied mathematics with applications of nonlinear optics, atomic Bose-Einstein condensates, material science with applications of granular crystals and fluid mechanics with applications, for instance, of free and rock waves. Today, he will talk about from nonlinear optics to UltraCold atomic physics and rock waves, adventures in applied and computational mathematics. Thank you very much.
Thank you, Simos. Thank you for the kind introduction. Thank you, everybody, for coming here. It's a great pleasure to be here. Perhaps as we start with the code, you don't know my training in physics. I have skewed towards computational mathematics and broadly applied mathematics. So although I'm a physicist by training, I have been trained later on developing numerical methods for studying such type of problems. So I will begin with my outline of my talk. So the motivation for my research comes from the study of complex systems in general, especially those that they have wave-like behavior. So we're talking about wave phenomena, some type of phenomena that can appear out of nowhere, disappear without a trace. Those are called extreme events or rock waves. Also, there are types of waveforms that can collapse or blow up in finite time. Quite important problems in optics when we want to propagate a light pulse through a medium. You want to know if this pulse over the course of propagation is going to collapse. But those are other types of waves that appear in atomic physics and going to macro waves. I will give you an overview about some models of merisms that revolve around. Those are the fundamental linear wave models. And then we're going to switch gears and talk about computational techniques, how to study those type of structures, starting from Newton's method. It's a root-finding method that you can solve nonlinear equations, systems of nonlinear equations. And what you can do also is that you can use Newton's method and combine it with some algorithms for performing continuation. So essentially, how can I find solutions as one or more than one parameters of my systems change? That would be the topic of numerical continuation. And then we're going to see some of its advantages, some of its limitations, and that will give birth to what we're going to call a deflated continuation method, which can factor out solutions that you know from your system, and you can potentially find new ones. Then I'm going to go through a survey of some of my results over the years about those techniques. Essentially, I'm going to do a study of the computational spectral solutions of substructures in nonlinear discrete models, chiefly the nonlinear centigrade equation of nonlinear centigrade systems in 2D and 3D, 2 components, and so on. But also the study of rock waves in discrete models, which can model a couple of waveguides where we started with the propagation of subatomic structures there. And then I'm going to wrap it up with the presentation of something like collapse, essentially blow-up solutions, how we can actually find those numerically, and what their spectrum essentially mean, and how it connects with the invariances of the system. Okay? So wave phenomena, those are disturbances that need the medium to propagate. Some elementary examples: if you're sitting on a pond and during a rainy day, you will see the falling of droplets on the pond that create those ripples that propagate. If you're lucky enough and you live next to the coast, as I am right now in San Diego, you can have also the interaction of wind that crosses the surface of the ocean, creating those ocean waves, quite fun structures for surface in particular. At the macro scale, we can also have such type of disturbances where you have a binary system that orbits around itself, creating those disturbances or those gravitational waves that can actually propagate to space-time. At the macroscopic level, the propagation of a light beam, when it encounters an obstacle, undergoes diffraction, meaning that it can split into different colors or different wavelengths, different frequencies, but also a structure that is quite important in my work is the particle, is the wave particle duality that actually convert to the quantum mechanics era. Those will be the structures that I will be very much interested in my work. Okay, so another type of beast that I'm very much interested in is those extreme events, those rogue waves as they call them. As I mentioned, those appear out of nowhere and disappear without a trace. Those are waves that they have a gigantic amplitude. Here is an example that I found from the Library of Marshall Wilbury, which actually demonstrates that it's actually, this is a small island actually of the coast of France. It's called Sun. So here you see the formation of suns and extreme event out of nowhere, this gigantic massive wave that can actually have catastrophic consequences if you think of, like, instead of having a lighthouse, you have a nonlinear reef. So it's quite important to understand those type of structures in order to protect our environment as well. So moreover, notice there are structures that actually there is this perfect balance that we very much hope to have in complex systems, especially when you have the balancing of two forces, namely the nonlinearity and dispersion. Dispersion itself tends to spread things out, and nonlinearity tends to focus things. So when you have this perfect balance of those two forces in code, you can create some localized solutions, or as we call them, solitary waves, that can propagate undistorted in nonlinear dispersive media. And as an example, one of the first experimental works by Nonlinear in the 1980s, here you can see the power of a light beam that of an incident wave actually that propagates through a medium, and past the specific threshold, you have the formation of a nice localized pulse, and then after a certain threshold, when you are at 5 watts, that actually pulse undergoes collapse. It has this very large amplitude. Applications of such waves can be found in nonlinear optics, mostly in the propagation of waves in optical fibers. People have started realizing the formation of a group of such type of waves, solid bursts. So also the collapse or the formation of such waves that they have this very large amplitude and eventually they can collapse. They have also applications in actually detecting the concentration of pollutants in the atmosphere. So that is called LiDAR. It's a very well-known experimental technique where people can actually throw such kind of pulses to the atmosphere, and those during the propagation, they start having a very large amplitude. They turn into filaments, and then through backscattering, they can actually measure the concentration of pollutants in the atmosphere. However, such kind of material structures have been recently started applied to neuromorphic computing. Essentially, you can think of a array of neurons that can establish synapses by the propagation of such material structures. Okay? Another thing that such structures emerge is the very well-known area of Bose-Einstein condensation, where it's a state of matter where which is formed when a gas boson is cooled down to 0 Kelvin. It was predicted many years ago by Bose-Einstein, and it was observed in 1995 by two groups, one in the Joint Institute of Laboratory Astrophysics, and the other one at MIT, where as we take a collection of atoms and we cool them down to extremely low temperatures, everything condenses, everything becomes localized. And for me, as an applied mathematician, I like to think of those type of structures as localized solutions to a nonlinear dispersive equation, where I have this balance between nonlinearity and dispersion. So, as an example of such a model where you have a balance of a nonlinearity and dispersion, I'm just picking the example of the Kurdyevich degrees equation, a very well-known phenomenon, a very well-known model in fluid mechanics. where the solution of this model describes the height displacement of the water surface from its equilibrium. It has a third order dispersion captured by this third order derivative and a nonlinear term. And surprisingly enough, this model, although it's nonlinear, it has explicit solutions, and the fundamental solution, the soluble solution, as we call it, is it has this form of a hyperbolic secant. C is the speed of this wave. It is a traveling wave, as it's shown here. It travels with that speed c. And many years later, a systematic analysis was carried out by Kraskell and Lubasky. Then it was the era of the inverse cavity transform, where you can write down a system of two linear differential equations whose compatibility condition becomes a nonlinear dispersive problem. And that linear problem has the nice property and gives us the information that such a model has an infinite number of conserved quantities. So if you have a model that has an infinite number of conserved quantities, that means that your system is integrable, or equivalently that you can solve this by means of functions in closed form. Okay? So that's one model. Another model is the nonlinear Schrödinger equation. So if just for the time being you disregard this term here, this nonlinear term, this is the linear Schrödinger equation in free space. But if you think of this model in the course of light propagation in nonlinear optics or in waterways or even in water-sand condensates, the nonlinear term appears there, which at the level of atomic physics that actually comes from interactions between atoms in your condensate. So that nonlinear term is there. Okay? So the model itself is integrable as well. This gamma is a prefactor that specifies the flavor of your interactions that you have in the condensate, or if you think of terms in optics, for example, if gamma equals -1, that means that you have a focusing nonlinearity, or attracting interactions if you think in terms of condensate, or if gamma is positive, if it is +1, then you have repulsive interactions. Okay? And at both limits, you can write down the explicit solution to the problem, namely the right solution, which is again has this form of a hyperbolic secant. It travels with speed c, and the gray Sullivan, which is the traveling wave solution for gamma equals +1. I should highlight that when the b equals to 0, then it becomes a stationary solution. Okay, it is called the dark Sullivan solution. Okay, another type of exact solution, since the model is integrable, the NLS, as I'm going to call it, we can describe those rogue waves, those extreme events that appear out of nowhere and disappear without a trace, as the one-parameter family of solutions. Here, you have an expression of your complex valued wave function psi as a function of x and t. Here, the model is integrable only in one spatial dimension, and you can have different type of localization based on your choice of this parameter alpha. If alpha is greater than 0.5, so now I will simply move this plane. So when alpha is less than 0.5, you have a spatially periodic solution. It sits on a finite background. The background is actually 1. When alpha is 0.5, that's a very special case of this solution. This is what we call as the Peregrine breeder or Peregrine solutor. It is a double localized solution, and when alpha is greater than 0.5, the solution itself becomes a time periodic solution. Okay? So this is a great candidate of describing such type of extreme events. Also, such type of events exist in discrete models. So if you have seen at some point finite difference approximations of derivatives, you may recognize actually that this is the second order accurate central finite difference scheme with the lattice spacing equal to 1. So you discretize your nonlinear Schrödinger equation with this finite difference approximation. That is the discrete nonlinear Schrödinger equation. This model is quite relevant in optics, where people actually use it for in experiments. But the model itself is not integrable in the sense that you cannot write down an infinite number of conserved quantities. However, Abelman and Ladek in the 70s, they came up with the integrable discretization of the NLS. Essentially, instead of having the mod psi squared times psi, they average the wave function at near neighbors, and that is an integrable model. And since it is an integrable model, you have exact solutions, namely the discrete analog of the Peregrine solution. And also there is time periodic solution that we have seen previously that is known as the Kuznetsov matrix. Okay, so again, we have a solution that is a finite account. It has a maximum at x equals 0 or n equals 0 in this case. And here is the evolution of this time periodic solution that oscillates with a regular frequency omega or period t. Okay. So those models now, especially when we change the nonlinearity, or even if we change the dimensionality of the problem, including also an external potential, which is quite relevant in experiments giving birth to the nonlinear Schrödinger equation with an external potential, or as is known, the Gross-Witkowski equation, together with the DNLS, but also the KdV with an arbitrary nonlinearity, where p is no longer 2, it could be 3, or any other value. Those models are not needed. So when we're dealing with such situation and we want to study those models, we have to resort to numerical approximation. So what does that mean? It means that you want to discretize your space. If you're dealing with a continuum model, for example, the Gross-Witkowski equation or the generalized KdV, you have to approximate your derivative somehow. You have to pose the problem on a lattice. Or if you have a discrete model, that's also fine. But at the very end, what we get a system of nonlinear equations. So essentially, we're solving a root finding problem, f of x equals 0. And in order to solve this problem, it's all about solving a system of linear equations. Is there anybody who has ever seen Newton's map? Or not? No. Okay, so just a crash course. So suppose that you have, I'm going to do that for one variable. So suppose that you have the graph of your function y equals f of x, and you want to find the point that this curve intersects with the x-axis. Okay? So, in order to find this point, Newton said, well, I'm going to start with some guess. Let me call this x naught. It's some initial point. I'm going to find the point on the curve. And what I'm going to do is that instead of attempting to find the point of intersection of that graph with the x-axis, I'm going to try to find the equivalent problem of the tangent with the x-axis. So I'm going to call this x1. Okay? So as soon as I have this point x1 that I can find, this is just a straight line. You can find also the x-intercept. You can then find the new tangent line to that graph, and then gradually you will start converging to the actual root of your problem, but in a very iterative way. So what you're going to get is a scheme that looks like this. In this case, if you just do this recursively, you're going to find that give me any nonlinear function, I will be able to find a better approximation to the actual root. So if I call this a star, by performing iteratively this scheme, and there is a close formula to do. Okay, that is Newton's method. Which you can generalize it in higher dimensions. You can actually consider a system of nonlinear equations that I have there. And in that case, instead of having this scheme, is going to be precisely the same. Now you're going to replace those with vectors. Okay, and this f prime is going to go afterwards. It will become f prime xk, and I have to write an inverse here, xk, and I'm going to replace it with vectors because I'm solving a vector equation, and that one essentially this f prime, in mathematics we're going to call this the Efstathios derivative, or just the Jacobian of my equations. Okay? So that's what we get. It's kind of a very nice iterative method for solving nonlinear equations. So if you want to solve this problem, this Jacobian matrix is essentially all the derivatives of your nonlinear function with respect to your independent variables. But the problem here is that in numerical analysis, you never invert a matrix. You never do that, especially when this matrix is large. Instead, what we can do is you can say that if I have the action of the matrix to the vector, that gives me a vector. So I can call this vector as pk, with the minus j this Jacobian metric times, let me use capital F since I'm using capital F, and that is inverse. And then instead, I can now multiply both sides with j itself. So the j times j inverse becomes the identity metric. So I'm just recovering. So let me write it simply like this. So if I want to find this vector p, which is the action of the j inverse to f, I just have to solve the system linear equation. So that is quite easy to do, in quotes easy. So that's what I'm highlighting here. That if you want to solve the system of nonlinear equations, you just have to solve the system of linear equations, find this p vector, okay, find this p vector, and then update your current iterate in this fashion. So that is one of the problems that we'll be interested in. The other problem that is quite important is when you want to study the response of a perturbation to a solution of the problem, which in fact results in studying an eigenvalue problem, which has this form. You have an operator acting on an eigenvector equals lambda times the eigenvector. My lambda here is going to be my eigenvalue. Okay. So the other type of a problem, if you want to study a complex system to a great extent, is you see if I have parameters in my problem, you can think of this as the number of atoms in the quantity. You can think of this as the speed of the traveling wave. All sorts of physical parameters that you have in your system. How can I study whether some solutions exist if I vary those parameters? So that will be the concept of numerical continuation, which I'm going to say a few words about this. So this technique is essentially all about developing a process, an algorithmic process of tracing solutions. If I have a system of nonlinear equations, which involves a parameter lambda, I want to see if I can find X star solutions to this problem as this lambda varies. Okay? So the natural approach to do that is if you know for a specific value of the problem, let's say lambda naught, if you know the solution, I can find the solution nearby by just doing some sort of a predictor corrector method, which means the following, that I know the solution is lambda naught. I'm going to move along the tangent of this curve of the norm x lambda plane, and then I'm going to use this tangent prediction as a guess to my Newton solver, and then I'm going to do a correction using Newton's method, and then I'm going to find the solution on that branch. So that is widely known as a sequential continuation or a predictor corrector. Now, the problem here is that if you encounter turning points, meaning that if you monitor, let's say, the norm of your solution as a function of your parameter that you vary, if you have this solid black curve and you encounter a turning point somewhere, meaning that you encounter a situation where you have a curve, this equivocation curve has a turning point. So at some point here, you have the concavity changes. So in that case, your Newton's method is going to fail because you cannot define the tangent here. Okay? So what can you do? You can do a different parameterization of the problem. You can actually use what we call the pseudo argument, the argument that we have seen maybe in the calculus course, where I'm going to think of x and my parameter now to be functions of the argument s, okay? And geometrically, so let me just not jump into the equation. Geometrically, what does this mean? It means that you have your curve, your bifurcation curve, if I make the curve that corresponds to the monitoring quantity as a function of your parameter lambda, and what I'm attempting to find is the point of intersection of that curve with the plane that it is orthogonal to this curve. So it is all about solving a problem that is my nonlinear problem that I had previously, and that one, this equation is the equation of the plane that it is orthogonal to this curve. Okay? If you just think of this as the normal vector of that plane, the normal vector of that plane consists of this x1 minus x0, lambda 1 minus lambda naught. So essentially, you just have this inner product from the equation of the plane. Okay, so we can do that, fine. And here is an example, like a one-dimensional example. Here you can use pseudo-argument continuation. You can actually cross that turning point, and you can trace this curve. Then one of the questions that we ask is that, are there more solutions to this problem? If you're brave enough and you play with different starting values, okay, with different starting values, I can pick any other x naught, I may actually be able to find another solution, which is not on that branch that I found previously. And if I do the pseudo-arithmetic continuation, which is capable of passing through such turning points, I can find another branch. The observation, however, is that those two branches are disconnected. Okay? So how can I systematically trace those two branches by just using one method? Is this possible? Well, the answer is maybe yes, and that is the concept of deflation, which combines numerical continuation and a process of factoring out solutions that you already know to your problem. Okay? So, suppose that you have a standing problem, this one, okay, and you fix lambda. So you treat now your problem only, your unknown is x, okay, and I'm going to find x1. I'm using my Newton's method, I'm going to convert to x1. And then what I'm going to do next, if I want to investigate the possibility of finding more solutions for the very same parameter lambda, I'm going to deflate the solution, which means the following. Instead of solving f of x equals to 0, I'm going to solve m times f equals to 0, where m is this operator that consists of two things. One is the x minus y, the norm of this difference of those two vectors to some power p. One actually the norm to some power p, which has to do with the following. Think of if Newton's method, if y, because here you have x1, this x1 is something that you know, this x now is your independent variable. If during the course of Newton's method, x is very close to x1, due to this term, it's going to actually push Newton's method away from that point that you know. So this kind of acts as a repulsive potential. It's going to push your Newton's method away from this. However, you cannot go far enough, because if you go far enough, that's going to be essentially 1 over something large. It's going to be almost 0. Plus, if I don't have anything, my m is going to be 0. So 0 times f is going to be 0, which means that Newton's method may erroneously converge to a trivial solution. To avoid this, you just add the shifting sigma. Okay? So those are two parameters that you can actually play with depending on the problem, and you can actually do this process recursively, meaning that if I find, let's say, a new solution to this problem, I can apply one more deflation operator for x2, and I can do this in such a recursive fashion for all the solutions that I will find on the problem. And then, if Newton's method does not converge at all, then I'm going to stop my search for that parameter lambda that I fixed, and then I'm going to vary that parameter lambda using the very same set of solutions that I have. And then I can potentially trace solutions to a nonlinear problem. So here is an example. So my initial guess is minus 0.1, I'm fixing lambda, it's minus 8. So if I'm minus 0.1, I'm going to convert probably to this solution. So Newton's method converges here. I'm going to apply this deflation operator for that solution, and I'm going to solve the deflated problem. So I'm going to find the second solution. I'm going to deflate now both of them. There is nothing in my problem, so my search stops. And now I'm going to change my value of lambda towards other values of lambda. So now I'm going to start heading towards positive values of lambda. If I do this and it's lambda, I will be taking those two solutions. One belonging in the lower branch, the other one in the upper part of that branch. So until I hit that value of lambda where I have those two solutions, plus I have the other one that belongs to the other branch. So now I'm able to start tracing systematically solutions that are parts of disconnected branches. So that is quite cool. At least it's not a magic bullet that can solve everything, but it can actually tell us something about more and more solutions to even a problem. So that's why it becomes interesting, because you can actually trace bifurcations, meaning that when your stability of a solution, or if I may, the stability threat of a solution changes, if you're stable and you become unstable, there's a bifurcation that happens there. So you change the stability characteristics. And one example of such bifurcations in the dynamical systems community is the so-called Pittsburgh bifurcation, where you are stable for some range of lambda, then your parent branch becomes unstable, and then it gives birth to two branches that are that are stable. So that is an example of a Pittsburgh bifurcation. So I can actually trace that type of solutions, right? I can use deflation to just trace those types of bifurcations. So indeed, in the context of matter waves, we considered a couple of years ago with Patrick Farrell and Efstathios, we considered the nonlinear Schrödinger equation with an external harmonic graph. And the solution to this problem, if you're trying to solve the nonlinear problem, there's no way that you can do that. You have to do numerics here. And in order to do numerics, first of all, you have to ask yourself what types of solutions are you interested in. I was interested in stationary solution. And since my problem is self-adjoint, I have a self-adjoint operator measurable by the class in here. I can use separation of variables. I can separate space and time. I'm going to get a stationary problem that's a boundary value problem. In particular, my mu is the chemical potential that controls the number of atoms in a condensate. And essentially, what I'm getting this nonlinear boundary value problem. So I have zero Dirichlet boundary conditions far away from the origin. Now, if I just for the time being, I ask myself, what about my initial guesses here? If I'm going to use an iterative method to find solutions here, what shall I do? Well, your initial guesses are provided by the following. If you for the time being say, if I take out the nonlinear term here, if I assume that the number of atoms is very small, that means that your nonlinearity is not important in your problem, you actually recover the very well-known problem of the quantum harmonic oscillator. So mu is essentially the other level of this. So you know everything about the system, you know the eigenfunction, you know the mu's, you know everything. So you can use that as your starting point to trace branchable solutions as a nonlinear regime that is controlled by the value of the chemical potential. The next step is to do stability analysis, meaning that you want to study the response of the presentation to a stationary solution, sign off and probably here. And epsilon is a very small parameter that I'm going to plug the entire thing here to my time-dependent problem. I'm going to linearize the equation, and what I'm going to get an eigenvalue problem that looks like this. Okay? So my calligraphical is this operator after linearizing the problem. So some results. If say I consider those linear eigenfunctions of my quantum harmonic oscillator, the ground state, I can actually trace it all the way to larger values of mu's. What happens is that here are the densities of the solutions. As I keep increasing mu, essentially, I'm having more and more atoms in my condensate, so the solution becomes fatter and fatter. Okay? Now, at the next excited state, the first excited state in particular, you have two possibilities. One is described by the product of two Hermite polynomials. It has 1, 0 crossing along the x direction. And the other one, if you work with polar coordinates, you can actually have a Laguerre representation of that eigenfunction that actually gives you what we call as a vortex solution. Okay, so you can continue the vortex solution all the way up to larger values of mu's. I can continue even that solution over larger values of mu's, but something happens here that gives birth to a solution now that has two actually vortices, and another one solution that happens a little bit later that gives birth to three vortices. So what happens here is that my solid blue lines are solutions that are stable, and by stable I mean that all the eigenvalues of that linearized problem are sitting on the imaginary axis. I can have eigenvalues that come as pairs where they have zero imaginary part, and the presence of the positive real part highlights an exponentially unstable solution because you will have an exponential growth here. Okay, and the other possibility with my green line in my curves, I have instabilities that experience both oscillations but with a growing amplitude. We call them oscillatory unstable solutions. So what happens here is that your pattern branch, this solution, as you keep increasing mu, what happens is that there is an eigenvalue that actually crosses the origin, it collides with another one and gives birth to an unstable one. Okay? So the pattern branch being stable, it becomes unstable, and the total branch is the vortex dipole, which is stable. So that is the example of the pitchfork bifurcation. Such a bifurcation happens later on, somewhere here, that gives birth to this vortex dipole. So there's another zero crossing, okay? You have an extra unstable mode, and then that process keeps going on. So we use this method, the deflated continuation method, as follows. You pick the ground state, you go all the way to very large values of mu, and then you use that to your deflation algorithm. You find the second solution, you deflate those two, you find the third one, you find the fourth, and that was actually a benchmark to just check with existing results in the literature. We found in total, I think, 65 or 63 solutions, I was wrong, 63 solutions, including 50 new ones, so those were never reported in the literature. And some results are shown here. If I have time, I may show you some videos about that. Main solutions are coming as bifurcations that the method was able to capture. And one of the interesting ways would be here we have some interesting results from the model. And the question is whether those results can be realized in experiments. Okay? That's something really interesting to me. One comment is that when you solve eigenvalue problems, there is, especially large ones, if you use MATLAB, for example, and you use eigenvalue solvers for sparse matrices, you may end up actually getting something quite nasty, as is shown here. In those two panels, these are the imaginary and the real parts of the eigenvalues as a function of my continuation parameter. And the reason that this happens is that those matrices, those mineralization matrices, for example, this one, those are quite sensitive in finite precision perturbation. So when you solve those eigenvalue problems, you may end up actually getting such type of stuff. So that means that your system is very sensitive. And in fact, I was kind of stuck. That was actually another problem involving two components that I worked a couple of years ago. And it was quite a dead end for me. I was stuck for a year in order to understand why I'm getting eigenvalues that are quite messy. And what I did, something that I'm telling my students, and something that I'm going to tell you, is that when you solve a problem, try to plug your solution to your problem, to the problem that you're solving. Let's say you solve an eigenvalue problem, you find eigenvalues at eigenvectors. Plug them back to the eigenvalue problem and see whether you satisfy the problem that you're solving. I did this and I found out 44.72. That's kind of a relative error, which means that what I got is totally trash. Okay? So what I then tried to do next was I wanted to be crazy with this thing where I was able to find a package where I can actually extend my 16 digits precision to 34. So for one computation, I was able to find such a relative error which is 10 to the minus 18. That's practically zero. Okay? But for each computation, it took 3 months. And I had maybe 50 brackets to do. So that was impossible. So what I did next was, I was quite thankful when I was a viewmaster, there was a professor at the computer science department who developed an eigenvalue solver called FEAST. It's based on contour integrals where you can find eigenvalues inside the contour. And that is actually part, or it should be part of the Intel's mathematical kernel library. If you have ever heard of it, it's a library that is part of the Intel's compilers and all this stuff. So I used that and I was able to get the same result in 15 minutes. So 3 months, 15 minutes is quite an improvement. I was actually able to compare what I got from this and what I got from this extended precision business. Fairly accurate compared to this one, right? So, of course, if you know a little bit about eigenvalue problems from the numerical part of view, you can actually bypass those issues that I showed you. You shift the spectrum by a certain amount. There's some algorithms that are called shift invert techniques. We can talk more about that if you're very much interested in this. So anyways, so that was the idea of the deflated continuation method, and we got really excited here now having the tools, continuation, Newton's method, robust eigenvalue solver. We went to three-dimensional setups, especially, again, one component, gross with X equation, harmonic trap, And we found some really cool solutions, namely a planar dark solid with a vortex line. So vortices now extended in 3D, two vortex line stars, all these beautiful vortex line configurations. And in fact, we were able to find a bifurcation in 3D. So here is kind of the number of atoms as a function of mu, and we found a bifurcation, a solution that comes from this planar dark solid with a vortex line perpendicular to that. This is a primary solution, although it is unstable. Okay, it is unstable. Even more, we got even more excited. We went now to a three-component velocity system in 3D, and those are quantum vortices called alipins, and using continuations, one can actually find extra branches of the problem. Okay, so that was quite a challenging problem. I mean, here you have like millions of unknowns because you can discretize your problem using finite differences or finite elements, pick your favorite discretization method. You end up with very large systems of nonlinear equations. So you have to have smart linear solvers, maybe using parallel computing. It is very, 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 very challenging task. Okay. So now, another applicability of such techniques that I told you is the study of those rogue waves. So now shifting gears from matter waves now to rogue waves, and thinking in terms of time periodic instantiations of that rogue wave that I call it as a Kuznetsov breather. That was in fact the work with my undergraduate student Jennifer Sullivan, where I was a DIMAS anchor, where what we did was the following. Suppose that we have the integrable model, that was the Abel logic that I showed you a couple of slides ago, and the discrete nonlinear integrated equation, which is quite applicable in optics, but it's not integral. You can construct a model that interpolates between those two limits. I'm going to call this the Salerno model. And for z equals 1, I have the integrable case where I know explicit solutions. For z equals 0, I have a non-integrable model that I don't know the solution. Now, I can think of those time periodic rogue waves. If the period goes to infinity, I'm going to recover essentially this peregrine solid solution, this double localized solution. So my starting point then is, if I want to find those time periodic solutions, my starting point is going to be some sort of a Fourier decomposition of my solution over time. So I'm going to use M Fourier modes over time. My P are going to be my the coefficients of that expansion, and I can actually plug this to this equation with the goal of finding solutions far away from the integrable limit. So if I want to say something to the experimentalists, I have to use the DNLS model. So can I find solutions to the DNLS that emulate rogue waves? So you do this approximation, you study the stability by adding a perturbation to it, you get now a system of differential equations for that perturbation. And if you construct the associated eigenvalue problem, you're going to get some information about the stability of those solutions. So here are some results on the continuation of such beasts when you start from z equals 1, the limit that you know your exact solution, and you use those continuation techniques, you can actually move away from the integrable limit. You cross it again, you cross it again, you cross it again. There is no way that you're going to go to the z equals 0 limit. However, the quite nice thing about this is that now you can tell to those people who work on integrable systems that, hey guys, there are more solutions to the integrable limit that you should actually look at. Okay? So such solutions, for example, are shown here. So where is this? The one, this one. This solution, C, is another solution that we found numerically, but there is no explicit solution, although it should exist because it is an iterable system. Now, if you're brave enough and you play with different values of your period of your solution, you can actually do something more. Indeed, when omega equals 10, we just have this bifurcation diagram. Essentially, we're monitoring the infinity norm of the modulus of the solution as a function of z, okay? And then after doing all this looping around the integrable limit, we were able to go all the way to the z equals 0. So that z equals 0 is one of the first solutions that I know of that exist in the DNLS model. So that is essentially what you get if you follow those configuration methods, that's what you're going to find, which is a novel solution in this sense. This has never been reported. Now, all solutions are unstable. Okay, those solutions are unstable. Here on those inserts, you may wonder, those are called the floating multipliers. Those are the eigenvalues of the so-called monotony matrix. So if you have any eigenvalues outside the unit circle, those solutions are unstable. So in all those cases, those solutions are unstable. And here is a direct comparison between the Apple-Islamic solution that we got and the VNLS one. Over the time propagation, those solutions are robust over many periods, I would say. So although are unstable, they may have some chance to be observed in experiments. So I think how much time I have? 5 minutes, okay. So in my last 5 minutes, I will actually give you maybe a very in passing discussion about the blow-up problem. Which means that if I have initial data in the nonlinear dispersive equation, the question is, out of those data, what are they going to do? Are they going to actually increase over time? Eventually, their L2 norm is going to actually go to infinity. What is going to happen? So the NLS in 1D, if you have a variable sigma, if sigma is not 1, that would have been the integrable case. But if you move away from that integrable case, you do have an exact solution, which is again the solution solution, surprisingly. And if you study its stability, what happens is that the solution itself becomes unstable after sigma equals 2. So you have a real eigenvalue that has a positive part, and that actually tells you that this solution then becomes unstable. So there is a stability analysis which I think I have to skip a little bit, which has to do with the following, that this instability gives birth to collapsing solutions. Essentially, that is the precursor of blow-up, meaning that my solution is going to shrink in its width, and then its amplitude is going to go to infinity. And the question then is, I'm not going to look at stationary solutions as standing waves. I'm not going to look at traveling waves, but I want to go in a frame where such a solution appears as stable. What does that mean? It means that I have to move with a frame that actually stretches in space, right? And also stretches over time. So I have to do some sort of a change of variables here, and I'm getting the NLS in a frame that co-explodes with the solution. Okay? So in that frame, this G that appears in the equation, that's the blow-up rate. It tells you how fast the solution blows up. Okay? Now, there are some other technical details that I have to skip, but what I want to say is that you can actually do a flow of this equation. You can actually pick solitary data, you can evolve it over time, and then after a large amount of time, the solution then appears as stable. Essentially, you have actually converged to a stationary profile, which in the original frame is going to be a blow-up solution. Okay? So with that machinery, then you can actually do a bifurcation analysis, because that's what I'm interested in. I'm interested in finding branches of solutions to nonlinear dispersive problems, in that particular case of blow-up solutions. So the soluble solution, when G equals 0, that is the solitary branch. When sigma equals 2, then the solution becomes unstable. And then it gives birth to those two branches that are the blow-up branches that are shown here, the real and the imaginary parts. So what we did a couple of years ago was actually tracking down what is the simplest ODE that can describe this bifurcation. It is not a pitchfork. If you have ever seen a pitchfork bifurcation, it has a cubic normal form, as we call it. This one has an exponential that is e to the minus pi over absolute g, which has this flatness here. Okay? So we tracked down all the eigenvalues of this problem, and we connected them with symmetries of the original problem. You have translations, you have phase invariance in there, and here is essentially the point spectrum, all the eigenvalues close to the origin that emanating from the localized pulse, and those are connected with symmetries. You have U1 invariance that was paired with this mode. You have spatial translation. So all the positive eigenvalues that appear in that co-exploding frame are nothing else than symmetry modes. So those solutions that we found are expected to be stable in the original frame. So there are things that I'm planning on developing in the next years. One is about studying collapse events and rogue waves. I'm very much interested in finite elements recently in order to compute those collapsing waveforms, understand their stability characteristics. This is an ongoing work with John Zappa at Oxford, with Michalis Kavousanakis in Athens, with Panos Kevrekidis at UMass, and Yanis Kevrekidis and John Hawkins at DARPA. And we recently did a very systematic tracking of branches in the generalized kidney paper, that is the paper that was published actually recently in Nonlinear, quite challenging problem, because here you have solutions that one behaves exponentially, the other one behaves algebraically. You have to use the accounting domains. That's the pain. It's really painful to resolve those solutions. And the other direction is about combining the displacement continuation method that I told you in order to develop a software in finite elements. There is a nice package if you are working with finite elements where we have seen of them. It's called FreeFan. It's an open source software that can do all sorts of nice things, measure activity, can solve very large eigenvalue problems. And this is going to work with people at Santa Fe Institute, Fred Cooper, with Albert Saxena, with Salomon Laboratory, with Yuri Danila, my host in Rennes, France, where I spent some time there to work on these problems. David Paul and Andres Collins, Simos, your colleague here, and Panos Kevrekidis at UMass. So I think I should actually stop here. Here is a list of people, of students that work with me and collaborators and that have my funding sources, and you for your attention. Thank you very much.
Thank you very much, Hans, for this nice talk. So please, do you have questions? Maybe first for graduate students.
You can ask anything, please.
So I have maybe two questions about this deflation method that you use to find additional solutions for your equations. The first one is, to what extent are you guaranteed to find all solutions that exist? To what extent are you guaranteed to find all solutions? All solutions.
You cannot find all. You cannot. I mean,
so
here, okay. So maybe this is a cheap answer. The convergence in Newton's method depends on how well you solve this problem, the linear problem. Now, in cases where this matrix has a large condition number, meaning that when it is quite sensitive, you have to think about preconditions, meaning that can I just find another matrix so that if I multiply the inverse of that matrix with this one, the new matrix that I'm going to get is going to have a smaller condition number, so it's going to be less sensitive, and I can solve this problem efficiently. So the finding a preconditioner is a whole research field. So as soon as you know something about the problem and a good preconditioner, it is quite likely that you will be able to trace more and more solutions, but not all of them. If I want to just be, clear.
Yeah. This was the first of the two questions. The other one, maybe I misunderstood this, but to me it looked as if you're adding extra terms to your problem to push the solution away, right? Can this lead to spurious solutions? The modified problems are not actually solutions.
Yeah.
Not actually solutions of the original one.
The models are here very well. So let me see. Yes. So in the modified problem, you just have two terms. One is that you do not converge to a trivial solution, right? Because you have this extra shifting. So that is not the case. And then you have the other one that moves you away from a non-solution. So you have the competition of those two forces, if I may. The thing is that you have to construct an operator that, number one, preserves the solution of solutions, preserves the set of solutions that you already have. That's the first property. And that operator respects that. And number two is that if you converge, if you find solutions of 0 to x equals to 0, that means that is a distinct solution. So no, which is not from the set. So that operator does have that. Now, if you want to consider something more exotic, perhaps yes. Perhaps yes.
But it's not a problem in the things you have been looking at.
No.
Okay, thank you.
You're welcome.
I did not quite get the transition from linear case to nonlinear case. I understand that if you have a nonlinear case, you can have like special solutions that are stable. But if we consider rogue waves,
Yeah.
these are transitory waves. Can they occur in purely linear system?
The answer is in a linear system, okay. So those rogue waves sit on a finite background, meaning that you have a constant solution that satisfies the linear problem, okay? Now, those localized solutions are mounted on top of them. So you have to have a non-linearity and a linear term such that those are balanced to each other, such that we can actually have localized solutions. So those are unstable anyways from the get-go because the background that are mounted on top is unstable anyways. So this is what we call as modulationally unstable solutions. Now, what I showed you here, maybe when you do that slide, I didn't comment about that, those floating multipliers. So all those instances that you see, those black dots here, those are the eigenvalues of the solution itself. But all the eigenvalues that you see, the real ones, those are not from the localized solutions, those are due to the instability of the background. So if you do a stability analysis of the constant solution, you find the eigenvalues of those of such solutions, and you overlay them with the eigenvalues that we get from such a solution with the very same constant solution, you will see that those are slightly perturbed, which means that if I mount such a solution on top of the background, it's going to slightly perturb those modes of the background. So those are unstable anyways. If that answers your question.
Well,
So always you need modulation and stable background to form rock waves.
You need
so
that.
there's no such thing as rogue waves in system.
I don't think so. I don't think so.
Next question. Next question.
Yes.
So you have to zoom in quite a bit to see those small
Say it again?
oscillations. No, those small oscillations.
Yeah.
Like, when do you differentiate whether these are small oscillations coming from the solutions, but not from the numerical inaccuracies? Like what is the way to look more into it?
Okay. So the first thing that you do is when you compute those solutions as time periodic solutions, so that is, of course, if you consider all those modes over m, over time in particular, you don't do this on the computer, you don't take all those into the main modes. So the approximation comes that you have to translate this summation, let's say m from minus a number to another number. Okay, so essentially you consider, let's say, a fixed number of Fourier modes in time. You plug this to your problem, you get that confounding problem, and you solve it. So this is an approximation for the error. How can you how can you say something about if the number of Fourier modes that I use is enough, or maybe enough to capture the solution that I'm using? So the answer here is if you solve the problem with a finite number of Fourier modes, you find its spectrum, its stability by solving this perturbation equations, the equations for the perturbation, and there has to be one eigenvalue, which has to be at 1 plus 0 times that. That means that when you have the your unit circle, okay, you have to have an eigenvalue here, and that eigenvalue is coming from the time translation invariance. So your model is time translation invariance. Just think of the derivative, the ddt, do a shift that t goes to t plus delta, your equations are invariant. If you have heard about another theorem, that gives you actually conservation laws, the energy, but that invariance is reflected to the spectrum. So you have a mode that is the 1 plus 0 I. you see how well you resolve them. If you resolve it well, the number of million model you use is enough. So that's one indicator. The other indicator is, since the starting point is at z equals 1, where you know the explicit solution, you can actually compare the numerics with essentially the numerical exact solution with the exact solution. You compute the norm and you see how well you have. Because that's the way. So you have some metrics which is just yeah.
Is there any next other question? No? Okay, maybe I have one.
Okay.
So in the last part, you saw these collapsing solutions. And
Yeah.
you argued that if I go to one dimension and I have my nonlinear Schrodinger equation, then I have to use more than a cubic nonlinear
Yeah.
term essentially, so that I see collapse, because otherwise one big collapse does not exist.
Here is essentially beyond me. Because sigma has to be greater than 2.
Yes, okay.
You want
You can learn the psi square times psi.
yeah, okay.
So my question is that, have you done this in higher dimensions where you
Yes.
have really, okay?
Yeah, that's essentially what I'm working on. The problem is there is a result for collapse that says when this product, well, when sigma times d is greater than 2, so d is the dimension of the NLS, so here is 1. So you have collapse when sigma is greater than 2, when you go to 2d, that means that when sigma is greater than 1 in this case. So I'm currently working on this, essentially tracking down those solutions as self-similar ones. As you can mention that when you go to this whole exploding frame, you just get the solutions that appear as self-similar ones. And the challenging part here is that those solutions, compared to the solid wave, if you look at the solid one, its explicit form, this is the hyperbolic secant, it decays exponentially, that's fine. Even if you do numerics, this is a nice type of solution. You don't need to use very large domains, you can use relatively small holes. But those solutions that appear as self-similar ones in this whole exploding frame, they have algebraic decay, which means that if you try to solve it numerically, you have to use domains from -2000 to +2000 in 1D. And to overcome this problem, you have to use compactified coordinates, something that I learned from the numerical relativity, that if you solve problems on cosmic space-time, you can actually map the linear coordinates, the 0 infinity to 0, 1, and you can solve the problem there. So if you now do this in 2D, it's even more expensive, because if you use a domain for -5000 plus 5000 squared, that's crazy. So I'm actually doing progress on this using anti-templates and method activity, because if you have an algorithm that can actually change your mesh where the solution changes more rapidly, I can actually use fewer points that are distributed in a way that I can actually resolve the solution, regardless of how small the decay of that solution is. I don't care.
And these are unstable solutions.
Good.
Unstable solutions.
Those solutions, the fundamental collapsing solutions, essentially, if you think of that solution, let's say if you think the real and the imaginary part rotated by 360 degrees, essentially 2D, this solution is stable in the original frame. So the solution itself undergoes collapse. But when the solution becomes unstable, when this stability threat changes, you have a bifurcation. And with that bifurcation, you have the emergence of 2 collapsing branches. One is with that positive G that blows up in forward time, and the other one in negative. In 2D, you have exactly the same picture. But the beauty in 2D is that you have more and more solutions. You have rings, you have
Exactly. Yeah.
you have other types of structures. Yes.
So these are modulation and stable as well, or what?
They are not. The thing is that they are not coming from. I'm not sure about that. I'm not sure about that.
Okay, we can thank our speaker.
Thank you very much. Thank you.
Yeah.
Okay.